All right, let's begin. Let me open my video. Yeah, okay. All right. So today we are going to talk about the EDA or exploratory data analysis, and this kind of analysis is really important in our preliminary stage of working with data, of understanding what are the distributions of our data is, and how can we express the data in graphical way to understand what are the internal structure of our data. And we are going to start with the everything is all right. We are going to start with the variation. So if you can remember, the variation is a tendency of a variable to change over time. And generally, we can measure some kind of value. Let's say it is the height of the person. And if we measure the height of the person, we have some kind of the instrument like the ruler. And this ruler has its own error measurement. And also, it depends on how the person stands. And if we measure the same kind of person 10 times, we'll have 10 different measurements. And this difference between the lowest and highest value will be the variation of the measurement of this person. The same kind of thing can happen if we measure the group of people, and each kind of person have its own variation, and the whole group of people has its own variation. All in all, we sum it up together. So today we're going to use this week 13, lecture 13. Do you see this code here, right? Someone, do you see EDA? Anyone let me know in the chat or hello?
Hello.
Yeah, do you see EDA? Do you see the screen sharing?
Yeah, definitely.
Okay. All right. So the same kind of week 13 lecture you have to. I provided this file over here. So week 13 lecture 13. So you can open it and you will see the same kind of thing. All right. Um, the we're going to use two packages here, ggplot2 and dplyr. Hopefully, these packages have been installed. If not, then you can use either these packages or just click the package install and provide the single uh, tidyverse. And tidyverse will install ggplot with dplyr altogether. So you can load either these two packages or the single package tidyverse, right? Okay. Here we have the same data set, which is called the diamonds data set. It's a pretty large collection of measurements of diamonds, and okay, make the chat somewhere different way, and let me put away participants. Okay. So you can see here in the right hand side the how many diamonds are there and what are their counts, how many diamonds of different cuts. So fair cuts is the best cut of the diamond. It's a really perfect diamond, and all the way up to I have got a really large monitor, so up to ideal. So fair, good, very good, premium, and ideal. So fair is the worst, ideal is the best. Um, we have uh, measurements, and you can see that the overall measurements are about 20 plus 15. So it's several several dozens of thousands of diamonds were measured, so pretty decent data set uh, to analyze. Hopefully you also are familiar with this kind of commands. The ggplot is really useful for us to plot something. Here we have to provide the data, and here we have to provide the aesthetics, AES. So aesthetics can be provided either inside ggplot or in our additional commands like geom bar. It produces this bar plot, and here we just provide what will be our aesthetics, what will be our x values, and x values will be cut. So we have provided the cuts to make our graph look like this. Also, you have to be familiar with this kind of notation. This is called the pipe. And pipe, we can place the pipe using the Control Shift M combination of keys. And this allows us to use the notation of like that. Diamonds, we place these diamonds to this function of count cut. So let me make the same kind of count diamonds and cut. It will produce the same kind of thing. Count is not. Oh yeah, it's internal deployer. Uh, internal deployer thing, we cannot use this. But the logic is the same. So we place this diamond inside some kind of the function. This is working because internal. The same kind of thing that we place some kind of data set or some kind of the variable inside the function. And this pipe is a special invention of one particular person who invited the diverse, the whole way of working with data, and especially the invitation of this deployer package. All right, so what does this command provides us? It provides us a table which counts the exact numbers of different cuts of the diamond. So this variable is continuous, and we can provide the histogram of this value. Each continuous variable can be plotted with histogram, and it's really useful for us to understand what the distribution of data is. What do I mean about distribution? The distribution shows us what is the preliminary value inside the data. So we can see in this particular figure that the majority of data is situated over here, and we have some kind of skewed data. It is not normally distributed. It is skewed to the left, and we have the majority of our diamonds situated between 0. Maybe 2 to 1 and 25, 1.25, I guess. Uh, 1.25 carats. So this is the majority of data. And if we are talking about the data as a whole, we can think of our data as only these two values, which are preliminary. And there are several kind of things that you can grasp from this this graph. And the single kind of thing is that you cannot just simply use linear regressions or something to produce the results you need. You first have to some kind normalize the data to make it more look like normal before you just use the modeling of the data. So this is the first option to use with histograms. So histograms divides x-axis into equally spaced bins, and we can provide this view of these bins. And let's say we need to group our data in some particular 0.5 carat lengths. So the first is non-reasonable because minus 0.25, but still, in order for us to get these equally spaced groups, we have to use a negative value. Instead of that, we not be able to have the same kind of zero point 0.5 between group distance. And you can see that the 0.25 belongs to the first group, as well as the 525 belongs to the last group, 11th. And we have got only one diamond in each of these groups. So pretty rare. And generally, we can leave those 8, 9, 10, and 11 groups away from the site, because these are just outliers. These are not representative in comparison to other groups inside our data. Of course, we can change the grouping like 0.25, and we will have more groups. And you can see that we have now 19 groups, and especially here we can leave only these values to represent our diamonds. So the majority of diamonds are before have size have weight less than 3.12 carats. Have weight less than 3.12. So this is just the cut width, and we select the variable over here. Let's produce. Let's load the data just to data. Let me use balance. So here is our data. This is the table. This is the measurements of this data, and we can see that the caret is just one column inside the data. So we can use different kind of columns. We can select the depth, table, price. Generally, caret is meaningful for us, and price is also meaningful for us. I think these are the measurements, but still let us use the help to provide the prices of 50,000 round cut diamonds. We have length in millimeters of the measurements. We have the clarities from infinitely great, very small inclusions, and so on, up to the worst. And we have the weight of the diamond from these kind of measurements, which we already found. And these are the prices in United States dollars. I'm not sure about the exact year when this data is collected, so we might multiply these numbers twice or even more. So what can we say? We can say that this first caret is the continuous variable. Price is also the continuous variable, and we can provide this kind of change in, let's say, price, but we still may have provide some kind of, maybe $100 is not the best choice, but maybe let's start with $500. And we can see that here are the measurements. So only 8,000 something diamonds fall into this cheap category, and still there are from 4,750 to 5,250, and there are 28 more rows. So this is just the preliminary way. Maybe price. Maybe we can cut the data set in parts, and let's say we need to analyze some kind of the diamonds which are more than particular price, let's say more than here is 18,000, more than 10,000, and just analyze this small amount, and we'll have the representation of how many diamonds fall into these categories. So it's up to you what kind of variable to define, and what kind of measure to place in order to group your to group your data into these categories. This is only for continuous variables, so you cannot do this with cut, because cut is the categorical variable. It is ideal, premium, good, and that's it. but groups can be made for continuous. All right, any questions here? If any questions, just place some words in the chat. I can see the chat. So these are, let me make it a little bit. Okay, so these are the smaller diamonds. How can we uh, separate uh, separate based on what we have found? We have found these values 275, 325, and to be more exact, it is about this value. So we can place like 3.12 over here, and these will be the smaller diamonds, which are really meaningful for us to analyze. And these are the histogram of the data without outliers. And we can see that here uh, with the parameter beam width, which is 10% of the regular width, we can see 10 times more bars inside the data. And inside this data, it is really useful for us to understand what are the certain peaks, and it is not that skewed distribution because we have a particular peak of 1 carat. Why is that? Because the majority of engagement rings are about this 1 carat, and we have this certain peak. And also, yes, the cheapest is the largest, and there are certain peaks of 2 and 1.5 carats because people like these, these values more than anything. And we can see that there are not that many diamonds in just before 1.5 and just before 2. So people prefer to pay a little bit extra to get this like 1.5, 2 carats for maybe for a gift. Maybe for in terms of investment, if the color is really clear and the cut is really ideal, so it's in terms of investment, it might be also a good option because diamonds are going more expensive and more expensive. Okay, how to place the histograms here in the same plot? So we can provide the histograms based on the cut of the diamond, and we can see that the color of the histogram depends on the cut of the diamond. And uh, here is the legend for this cut, and we can see that the ideal cut, it's not really great to see on some monitors, but still the peak is over here. It goes all the way right there, and we can see that the once we move from the low low weight of the diamond to higher weights of the diamond, we can see that the price, the number of those diamonds becomes more equal. So the real change in the quantities uh, is before 0.75 carats, I would say. So what really we are doing? We are thinking of the EDA, the exploratory data analysis. So exploratory data analysis belongs to the understanding. It covers the understanding of our data. So we have to visualize, transform, and model our data, and learn some particular parts of our data based on the questions that we ask ourselves. So we ask different questions. What is the distribution of the data? How they vary? What groups can they fall into, and so on and so forth. And based on that, we build some graphs, and using these graphs, we understand what is the internal part of our data. So after the general look over the data, we have some kind of the typical values and the unusual values. So typical values, we are going to use different data set. So it's pretty normal. The data set is called faithful. We can see what is the internal part of this faithful data set. This is the geyser data, waiting time between the eruption of geyser. We have 272 observations, and only two columns, uh, time in minutes of the eruption, so the geyser erupts, and waiting time in minutes between the eruptions. Really easy to understand data, and we can see that here is the how many eruptions were, and the majority of the eruptions is about 4 to 5 minutes. And we can see that there are two, like the bimodal data over here. We cannot model the whole data set with the single equation. We have to use two equations, separate the data somewhere here, and model this kind of distribution separately and this kind of distribution separately. We have two models, and using this model, there is like the ensemble of this model, the unity. And if the value of um, the some value, some data characteristics falls into one category, so we can uh, predict the duration of the eruption based on those characteristics using one model and then using another model. So it's pretty, it may look pretty overwhelming, but here the modeling part is placed on the other side. Maybe we will cover some basics in our last lectures, but for now we just need to graph to understand how to provide how to produce these plots. Okay, geom histogram, geom free poly, and what else? And geom bar. These are three types of graphs we have produced so far. Histograms distribution, frequency polygon is also the distribution. The polygon just let me use this. It just unites. It just makes the line between um, the middle part of the each bar, and it provides the polygon, which is the line. So okay. Um, Typical values, these are just the typical values. Unusual values are called the outliers, which stands either on the lowest part or on the highest part of the graph. And to understand it, we might use, uh, I don't see why we haven't used, but generally to get the outliers, we need to use the box plots. Maybe we'll use it a little bit after that. So the first option about the unusual values is looking at this kind of data. It's not pretty obvious, but if y variable here uh, stretches in this direction very far, that means that might be some kind of value, and we simply cannot see it. We can see some really small value, about zero. Over here we can see some small values over here, but we cannot see, but maybe there is some value really far. And geom histogram is really difficult to see. It's really difficult to use to show us the outliers. But we might normalize, or just limit the certain value of the histogram. So this histogram is the same as this histogram, but here in the first one, you can see 0, 4,000, and so on, the count. And now we just limit our histogram to produce only first 50 values of counts. So how many are situated in these 50s? And we can see, yes, there is certain, maybe we can even, this meeting will end in 10 minutes. So in 5 minutes, we will reconnect. Um, so we have these kind of value, we might limit it to 10 and produce this histogram and see, yes, there are certain amount of values which is less than, which is slightly more than one. Um, one way to spot these unusual outliers, and generally you have to remove these outliers because each of these outliers spoil the whole distribution of your values. We will show how to remove later on. Next, unusual diamonds. We can also provide these several commands. And we start with the diamonds. We filter them based on this y value. Y value is this value over here on the x-axis, and y value less than 3 or y value less more than 20. So we separate very small values and very large values and arrange them and place them in the variable which is called unusual. And here is the unusual. It has only 9 unusual values, and we can see what are these particular diamonds look like based on the unusual y value. And we can see that the premium cut of the 2-carat diamond with slight inclusions, and it has a really large y value, and generally the majority of diamonds do not have this. So we're talking about round diamonds only, and this is not round. Missing values. For unusual, we just need to remove all these 9 values because we have 58,000 observations, and these 9 values are neglectable in comparison to the whole amount of observations. But if we have only like 100 observations, 9 values is 9% of these 100 observations, and generally it's not a very good idea to just remove them. It's a good idea to change those values somehow. Maybe just the mistake, maybe we can analyze this mistake and replace the value which is too far. Maybe we measure the weight of the puppy, and the puppy weighs like 50 kilograms, and it is impossible. Maybe it is 5 kilograms instead of 50, and we can just fix this mistake by ourselves. It's a better way to deal with these outliers. So for missing values, if you encounter unusual, we can filter, and this filter is the same kind of thing as here. So between 3 and 20, and now our diamonds is the data set which is equal to diamonds without these 9 observations. Okay, because unusual is only 9 observations which are less and more than those borders. So here, diamonds 2, we can see over here to the right hand side the original data set, the diamonds data set. We can have 53,940, and we removed 9 observations. So here it is without these 9 observations. All right, let's reconnect. Sorry for this, but we have to reconnect each 35-40 minutes. All right.